Alright, hello everyone and welcome back to another programming challenge. This is going to be a little bit of a Christmas special. Today we're going to be, this is not going to be like only for Christmas, it's just going to be applying an algorithm to a Christmas related thing. It's just my poor excuse to make a video on Christmas, but yeah, today we're going to be looking at minimum heaps and what they are, how you can use them, and then we'll be applying them to a specific Christmas related situation. So what we're going to be looking at today is, just share my screen, should be looking good. Yep. Alright, so on Christmas, you might have a rough time determining which gifts to open first, and you might determine, okay, let's save the most expensive gifts for last. So the gifts with the lowest prices this is just a stupid example, but and of course the value of a gift is only determined by its monetary cost, but anyway, so the price of a gift determines the order in which these gifts are going to be opened. Now you could create a sorted list. You could do that, but then there's also called something called a priority queue, where you assign different elements of priority, and this is more dynamic than a list, or than a sorted array. Because you can also use minimum heaps to kind of do other things, like incorporate it with a binary search tree, but we're only going to be looking at a minimum heap today. So priority queues, which are represented with heaps, and what they are is they are complete binary trees. So each element will have some value, and it will have maximum of 2 children. And the property that makes it a minimum heap is that the value of a parent node must be less than the values of its child nodes. So this is not a binary search tree. A binary search tree would just would essentially just put the smaller elements on the left and the larger elements on the right. But this is we're just giving it a priority queue here. So essentially that element in this small heap, the element with the highest priority would be the 1, since it is the head and it has the smallest value. And if we're equating small value to priority, then this has the largest priority. And then another property about this minimum heap is that in the binary tree, it's actually a complete binary tree. And that means that each level, so we have level 0, level 1, each level must be filled completely before moving on to the next level. So we can do this, add 2 more nodes, but we can't give these nodes children until we give the 5 2 children. And once again, they will be greater than their parent nodes. And then what this also leads to is that every single node is flushed to the left. And to represent this, there are 2 possible ways. You could use a binary node structure, where you just have a value, and then a left child pointer, and a right node. So those are the 2 different ways. Or that's the first one, and the second one is, because this is a complete binary tree, we actually get index relations. So if we were to represent this as an array, for example, if we had an array of items here, and let's say the first element was a 0, and this is just going to make expanding the array more easier. So if the first element is just 0, or just a null value, it's just there as a placeholder or as a padding value, then we have 3, 5, and I'll just say 7, 8, 6, 9. Oh, that's a funny number. And this would be represented in the array with 7, 8, 6, 9. So each level is filled completely before moving on to the next one. Oh, I actually forgot the 1. So this is incomplete, actually. And then you might also see, okay, well, now we need to expand the array, and the only times we need to expand an array is when a level is failed, or when a level is filled. So it's going to be multiples of 2. So we'll start at 2 to the 0, which is just 1, and 2 to the 1, or actually it's going to be the total number of slots in the array will be the sum of all these values. So 2 to the 0 plus 2 to the 1 plus 2 to the 2, which is equal to 2 to the 3 minus 1, but because we have that padding value in there, it just becomes 2 to the 3, which makes resizing it much easier. So that'll be the resizing if need be. And then, yeah, so then there's going to be, and then for the actual index relations here, the reason why we have these index relations is because we just go top to bottom, left to right. So the top level, then the second level, go left to right, then the third level, and we go left 7, 8, 6, 9, left to right. And what this gives us is that the index of a parent is equal to, let me actually make sure I'm doing this right. Or we only care about, so the index of the left child is equal to 2 times the index of the parent. Is this going through? Yeah, it's going through, right, good. And then the index of the right child is equal to 2 times the index of the parent plus 1. So each node is essentially paired with its sibling, save the root and a leaf node that doesn't have a sibling. But everything else must have a sibling, and it's paired with it essentially. So we're going to have a few operations here on this heap. First one's going to be add, and the way we're going to add is we're just going to insert it into the last slot. So insert into last slot in the array, and the array is more efficient in terms of memory storage, and it just makes it easier to manipulate the tree or the heap. So you insert it into the last slot, and then if you need to sort it, then you just perform something called upheap. And what upheap is it just moves the element, or just swaps the element with parents. It swaps parents and children if the priority of the child is less than the priority of the parent. And just an example here is if we were to insert, say, a -2, which could be, or I'll say, let's make this a 2 up here, and then let's say we insert a 1. What happens is we're going to want to swap this one with the 7, and then it's still lower, so we swap it with the 3 with its parent, and then we go to the 2, so the resultant is just a 1 at the top, and then a 2, 3, and then 7. And then the rest of the tree. Yeah, alright, so that's up heap, and then for popping, pop will be removing the element with the highest priority. And like I said, the highest priority will be the root of the tree, because it has the smallest value of any node. Because if a node has a value that's smaller than its children, and the root has the root is essentially the parent of all children, or the ancestor of all children, then it must be the smallest. So pop will remove the root, or we're going to return the root's value. And then we're going to substitute it with the last node. And then after that, we're going to perform down heap on the last node. And down heap is essentially the opposite of up heap, where we just swap we're performing the same swaps, except we're going in a different order. So this goes from moves upward, so it keeps track of the child, while down heap moves downward and keeps track of the parent. Like that. Ooh. Alright, so those are going to be the two functions that we'll implement today. Alright, let's jump into the code. I've been enjoying doing a lot of these data structures in C lately. It's been, and the reason why I like doing it in C is because of the memory management. It makes it, you can really harness a lot of, you can just custom fit pretty much everything to your liking. So we'll have two files here, hashmap.h and hashmap.c. And then we just want to go ahead and print out the, wait, no, not hash map, sorry, that was a mistake. It's min heap.h and min heap.c. And then we just want to add min heap.c to the build path. If you're doing this in an IDE, it already does that, but I'm using GCC, a command line compiler, so I just need to make sure that it compiles everything accordingly. Alright, so we will start with our, in minheap.h, we'll start with our macros. So if not defined, minheap.h, define min heap h and if, and then we want to define another macro here. Define default num or default array size, and we'll say 4. So that's just going to be the number of elements that we start with in the array. And then we'll, for a structure, we'll say type def struct min heap. Or, yeah, just the min heap structure. And then name it min heap. Then we'll have just 2 values here. Or we'll actually have 3. So this is going to be much like the dynamic array, where we have a size, a capacity, and then the array. So unsigned int capacity, and then unsigned int size, and then for the array it's just going to be a void double pointer heap. And this is, we've seen a void double pointer before. It's just a generic array, pretty much. It's an array of void pointers, and the void pointers can be anything. All right, we'll have a few allocation, I actually don't know how many allocation methods we'll have. Let's see. I feel like we could just get away with doing one. So yeah, we'll have one. So min heap, and then I'll call it m heap allocate. And oh wait, we do need to have one more thing. We need to have a comparison function. So in the structure, we need to have a function callback. So it will return integer, and we'll call it entry CMP for entry compare, and then pass in a void pointer val1 and a void pointer val2. And then for allocate, we just need to pass in that function callback. All right, I'll first start with two, or actually, sorry, I forgot this, but along with the allocate, we need a reallocate method if we need to resize. So that's just going to be return type void, and it'll m heap underscore reallocate, and we'll pass in a min heap pointer heap. All right, so those are going to be the two allocation methods, and let's actually just go ahead and define these. So in minheap.c, we need to include minheap.h. And then for the other includes, we need system includes. So include stdlib.h, include stdio.h, and that's it. We might not even need stdio, but I think we'll just leave it there for now. All right, let me copy these definitions or the signatures, and I'll paste them in. All right, for allocate, what values do we have? So I'll create a min heap value for ret, and then ret.capacity is equal to default array size, and then ret.size is equal to 0, and then ret.heap is equal to malloc of ret.capacity times size of void pointer. That's just a void pointer array. And then we also want to set the initial element to null value. If you remember, that was just a padding element, just so the math would work out a little better. So ret at 0 is equal to null, and then we want to set the function callback. So ret.entry compare is equal to entry compare, and then we want to return ret. All right, for reallocate, we just want to have an if statement to determine if we should actually reallocate something. So if size is greater than or equal to, if heap.size is greater than or equal to heap.length. So it's assumed here that you increase the size when we push something, and then we determine if it needs to be, if the array needs to be resized before actually adding the element. So this will set the array to something that can add another element or another level in there. And then all we're going to do here is we're just going to multiply the length by 2 until it's large enough. So integer or unsigned int new length is equal to heap.length. And while new length is less than or equal to heap.size, new length bitwise shift left equals 1. So we're just going to shift the bits over by 1, which multiplies the size by 2. Oh, did I say length? That should be capacity, yeah. It should be heap.capacity. And then what we want to do now is just create a new array. So we can have a void pointer new r is equal to malloc of new length times the size of a void pointer. And then we're going to copy the elements. So for unsigned int I is equal to 0, I is less than heap.size, I++. And then new r at I is equal to r at I. Or, sorry, is equal to heap.heap at I, sorry. And then after this we can update the pointers. Or actually, what do you want to do here? So what we should do actually is create, like we did with the, or not like we did, but we should create a temporary list to swap them, because we want to free the actual array that already exists there. So we'll say void pointer tmpr is equal to heap.heap, and then heap.heap is equal to new array, and then new r is equal to temp r, and then we want to free new r. And then we want to update this capacity of the heap. So heap.capacity is equal to new length. Alright, so that's the reallocation method. It just takes values and copies them to a larger array. That's pretty standard. Alright, now for two utility methods, we're going to have a... oh shit, what was it? It was... it was a swap method, and then I was thinking oh yeah, and then a compare method. All right, so we'll have a void mheap swap elements, pass in a min heap pointer heap, and then pass in unsigned integer idx I1 and an unsigned integer I2. This will just swap the pointers at both locations. And then we want to have a... oh shit, I forgot it already. I said it literally 5 seconds ago. Oh yeah, the compare. Alright, so integer key compare, or entry we're going to call it entry compare, and we'll pass in indices now. So min heap pointer heap, unsigned integer I1, unsigned integer I2. So the function callback that exists within the heap structure will compare two keys, or two values, but we have to pass in the values. And then in this function, that will essentially just call the function callback with the values at the indices. All right, so for these two methods, swap elements, we can just create a temporary variable, pretty simple. So void pointer tmp is equal to heap.heap at I1, heap.heap at I1 is equal to heap.heap at I2, and then heap.heap at I2 is equal to TNP. And then for entry compare, it's just going to return heap.entryCompare and pass in the values at these indices. So, or we actually have to test to see if the index is valid. So if I1 is greater than or equal to, or it's just, ooh. If I1 is greater than heap.size, or I2 is greater than heap.size, we're going to return 0, and then otherwise we'll just return heap.entryCompare, so to use the function callback using the elements at those locations. So heap.heap at I1 and heap.heap at I2. Just need to check my phone real quick. All right. All right, so those are the two utility methods that we'll need. And then now for the operation functions. There's going to be 4 of them, and then we'll do clear at the end. All right. So one is going to return void, and we'll call it mheap underscore. Ooh, I misnamed this method here. I just didn't put the, oops, shit. Didn't put that in there. Alright, so mheap add, and we'll pass in a void pointer value. And then we'll have the actual down heap, or we need to pass in the min heap pointer as well. And then with the add, we have up heap, so we need to also put that method there. This returns void mheap. We'll call it on up heap, pass in a min heap pointer, and then an unsigned integer index. And then we'll have void mheap pop, which will remove the top element, and we'll just pass in a heap pointer, and then void mheap underscore down heap, min heap pointer heap, and an unsigned integer idx. Alright, so these are going to be the functions that we'll implement now. Alright, we'll start with add. So we need to increase the size and resize if necessary. So heap.size ++ and then resize. Or resize and pass in, or sorry, mheap underscore reallocate and pass in the heap. And then we want to set the next slot, or next open slot to the value. So heap at size is equal to key, or is equal to val. And size has been increased, so it represents the next one. And if you remember, or this does not, we're not counting from 0, because the 0th element in the array is technically just a is just a padding value. This should be heap.heap at size. And then we want to up heap. So mheap underscore up heap and pass in heap and size as the index. Actually, this should not be size, it should be heap.size. Alright, now for upheap, we're gonna do something here. So we're gonna say while idx is greater than 1, so just we're setting a lower bound on the index, and heap or key compare, sorry, heap dot entry compare. Oh, I'm speaking out of my ass right now. I don't have C implementation. I have Java implementation that I'm looking at, so it's a little. I'm translating it, but I'm forgetting about functions. So we need to compare. We need to have a lower bound, and then also compare the values of the parent and the child. So we're going to say and mheap underscore entry compare. Pass in the heap, and then the indices that we're going to compare is idx and idx divided by 2. And that must be greater than 0 for it to be greater. So I'll write a comment right here. So lower bound, and then compare child, which is at idx, with the parent, which is at idx divided by 2. Doesn't like this. Okay. And then while this is true, we're just going to swap the elements. So swap mheap swap elements, pass in the heap, and then the indices that we're going to swap are idx and idx divided by 2. And then we want to update the index, so just divide it by 2, or we can say idx right shift equals 1. So just right shift by 1, which is just dividing it by 2. And this division by 2 is tracking the parent. So we're essentially moving our pointer up the heap. And that's why it's called upheap. Alright, for pop, it's going to be relatively straightforward. We're going to have a void pointer ret, which is equal to heap add 1, which is just getting the root node. And if ret, we're going to want to substitute with the last node. Or if ret, if ret and size is greater than 1, then substitute with the last node. So heap at, or sorry, I keep forgetting my class pointers here. So heap dot heap, and then heap dot size. So we're going to substitute with the last node. So heap dot heap at 1 is equal to heap dot heap at heap dot size minus. So we're subtracting 1 from the size and substituting it with the last node. And then we want to perform down heap on the new head just to sort it if necessary. So down heap and pass in the heap, and the beginning index is 1. And then we're going to we're also going to have an else if heap.size is equal to 1. And then in that case, we're just going to set the pointer in the array to null. So heap.heap at 1 is equal to null. And then otherwise, or not otherwise, but outside of the if and else if statements, we're just going to return the value. So return ret, which could be null very well. Let me just refill my water real quick, sorry. Alright. Now for down heap, it's going to be a little more complicated than up heap. Because if we're moving a child down, or if we're moving a parent down, we're going to have two possibilities. You can either swap with the left or the right child, and we have to determine which one. Alright, so we're going to say, for down heap, we're going to say unsigned int I is equal to idx, or, sorry, we actually don't need that. We're just going to have a void pointer child as a placeholder. And then the while loop will be while, while child. Ooh, sorry, one sec. This should not be a void pointer, this should be an integer, an unsigned integer, because we're using it to represent the index of the child. So while child is equal to, or while child equals 2 times I, and that is greater than, or is less than or equal to heap.size, and this just means left child exists. It just means it has a left child. Or this should be 2 times idx. Oops. Alright, then we're going to say if child is less than heap.size, then we know for sure it has a right child. And as a result, we want to swap with the large child. Swap with larger child. So if map dot, or sorry, I need to figure out which function to use here. M heap underscore entry compare, pass in the heap, and the indices will be child plus 1, and child is greater than 0. This means that the right child is larger. So we want to increase the child index by 1. So because we want to swap with that child. And the reason why is because let's say we had. Oh no, you don't want to see that. That was my control panel. So let's say we had this situation here, and we had the 5, the 6, and the 9, and we removed the 5, or we were swapping the 5 and the 6, or sorry, we were just performing down heap on the 5. Then we would say, or you know what, actually better example that actually would happen would be doing down heap with the 2. If we just blindly down heap to the left and swap the 2 with the 3, then we would get something that whereas the 3 is the parent and it has a children of 2 and 5. However, that violates the min heap because, or wait, would it? No, that's a bad example. I'm sorry. If we swapped, let's say this the 3 was a 13, and we swapped it, then it would be a 13 in the top. Wait, that wouldn't even make any. Wait, would it? I'm sorry. Wait, let me think about this. Let me draw an example. So let's say we had 15. So this is a valid minimum heap, right? Oh wait, no, is it? No, it's not. Let's make this. That's a valid minimum heap. So if we called pop, that would remove the 15 and substitute it with an 8. And I also forgot to, or you don't know, it's fine. Then the 8 goes up there, and then we want to perform down heap on the 8. If we just blindly move to the left, so then swap the 8 with the 3, what we would get is a 3, then an 8, and then a 2, and then a 9. Everything is okay but the 2 here. So we have to determine which of these children to swap with, because it should be a 2 in the top. Alright, and then we want to determine if the child swap is necessary. So if M heap underscore entry compare, pass in heap, and then child, and then IDX, if that returns something that is greater than 0. Oh, wait, sorry, this should be if we want to swap with the smaller child. Sorry, I'm looking at something else. But this should be if the first if statement the first inner if statement in the while loop should be M heap entry compare pass in heap child plus 1 and child. That should be less than 0, because then the right child would be smaller, and that's what we want. And then if the child swap is necessary, so if entry compare returns something that's less than 0, then the child is smaller than the parent. So if it is, then we want to just call swap. So M heap underscore swap elements pass in the heap, and the 2 indices are going to be IDX and child, and then we want to update the pointer, or update our index. So IDX is equal to child. And then otherwise, everything is properly stored, so we can just break. Alright, so that's down heap. I'll just leave that there for a second. And once again, just make sure that, or I should actually, oh my god, I'm sorry, I also made the mistake up here in up heap. Entry compare should return something that is less than 0, because we want to find if the child is if the parent or if the child is smaller than the parent. Alright, so that's down heap, and then now we'll have just 2 simple cleanup methods here. So void, or actually, sorry, I forgot something here. Pop should return a void pointer, because we want to return the value that was actually popped. And we actually have the return statement in there, I just forgot to update the return type. Alright, for cleanup methods, we're going to have void M heap underscore free, pass in a min heap pointer heap, and then void M heap underscore free deep, and pass in a min heap pointer heap. And for these, we're simply going to iterate through the arrays, and then we're just going to iterate through the heap arrays and then reset values. Alright. So all we got to say here is in just regular free, we're going to say free, pass in heap.heap, and then heap.size is equal to 0, and heap.capacity is equal to 0. And then for free deep, what we're going to do is we actually have to iterate through the elements in the list. So for unsigned integer I is equal to 1, I is less than or equal to heap.size, I++. And this is the weird syntax because, or the weird loop boundaries, because once again we have the padding in the front to simplify the math. And then we say free heap.heap at I, and then outside of the loop we're just going to call the same thing. So we can actually just call mheap_free and pass in the heap, just like that. Alright, that looks pretty good. Let's go ahead and test it with our Christmas scenario. So in main.c, let's go ahead and include stdio and then include the Min Heap header. And then int main, for int main, we're going to create a Min Heap. So Min Heap h is equal to mheap_allocates. And we actually have to create some sort of value to compare, so we'll have a structure here. So struct, and we'll call it a gift. And we should actually say type def struct gift. And then the gift will have a double price, a char pointer giver, and char pointer receiver. And then allocate, well, then we have to create a function callback here to return an integer, and it will be gift compare. And we'll pass in a void pointer gift1 and a void pointer gift2. And then we want to return the conversions, and we want to compare the prices. So return gift1, or sorry, we want to convert the void pointers to gift pointers. So let's say G1 and then G2, and then we'll have in the actual method, we'll have a gift pointer gift1 is equal to the gift pointer conversion of G1, and gift pointer gift2 is equal to the gift pointer of G2. And then if gift1 dot price is greater than gift2 dot price, return 1. Else if gift1 dot price is equal to gift2 dot price, return 0, and then else return -1. And then we will allocate the mheap with gift compare. And then I'll have an array here of values just to make it a little easier with the pointers. So I will have gifts, and it will be size 10, I'll say. And then for each gift we need a price, and then 2 names. And then I'll just copy this 10 times. I'll actually, yeah, there we go. Alright, then for the prices, we'll have 10, 12.0, 15, 102.90. We'll have 1129.50, 56. Then we'll have a $1, 50 cents, 13.45, 234.12, and the last one will be 98.23. And then we'll iterate through the list. So for unsigned int I is equal to 0, I is less than 10, I plus plus. We're going to say h, or M heap underscore add, pass in a reference to h, and the value will actually be gifts plus I. This is just pointer arithmetic here, and it will just advance the pointer I spaces. So gifts plus 0 will be the 0th element, gifts plus 1 will be the first element, and it's like index or array indices. And then at the end we'll call M heap underscore deep free, or free deep, and pass in reference to h. Alright, let me try debugging this first just to make sure the pointer arithmetic actually works. So debug. Oh, alright, didn't like something. 14. Oh, okay, yeah. So in allocate, I said ret.0 is equal to null, but it should be ret.heap at 0 is equal to null. Oop. Alright, so we'll break at 47, then run, and I'm just going to try printing it just to make sure the pointer arithmetic works. We're going to say print gifts plus 1 dot giver. Giver 1, okay, so that works. Let me actually quit this. I'm gonna create a or how do I want to do this? Shit. I don't know if I want to do it, or you know what, we can just we're okay here. So let me just get the, or I'll add another method to print out a gift. So void print gift, pass in a void pointer gift, or g gift. And then we'll just print out g dot, or gift dot giver gave gift dot receiver a gift worth gift dot price. Doesn't like this. Oh, gift val. Alright, so we'll print out gift, and we'll pass an M heap underscore pop. Just gonna work. Oh, and we have to pass in a reference to h. Alright, so the most expensive, or the least expensive one is giver 6. So run. There we go. Giver 6 gave receiver 6 a gift worth 0.5. Now let me try doing this for all 10, and then we'll see what happens. So for unsigned int I is equal to 0, I is less than 10, I plus plus. Okay, there's an infinite loop, but it seems to be sorting them properly. 0, 1, 10, 12, 15. All right, so that was working, but I guess something else happened. All right, let me actually. I'm gonna walk through this, just so I can see what the heap should be, and I could actually just make this wrong. All right, so we insert a 10. Then we insert a 12. Insert a 15. Insert a 105 or 102.9. Then insert 1129.56. Then a 1.0, so that's going to be inserted here. But after some swapping, we're first going to swap up here. So this should become a 1.0 and this should become a 15. And then we have to swap again. So this becomes a 1.0 and this becomes a 10. So the resultant should be a 1.0 on the top with 12, 102, 1129, and then 10, and then 15. Still a complete binary tree. Then a 0.5 over here. Same type of deal, swap here. And we just get a 0.5 on the top. 12. 1. 102. 1129. And 15 and 10. Then 13.45. So that's just a simple swap. 102. 13. Alright, this is going to be great to write all over again. Then 1, 15, and 10. Alright, then we insert a 234, which is over here. That's a simple swap with its parent. And I will actually just not rewrite it all, just write in the replacement. And then a 98. And this will swap up here. Alright, so our ending array should have 0, 0.5, 1, or not 1, 12, 1, 13, 98, 15, 10, 102, 1129, and then 234. Alright, so let's run, or let's break it actually after we add all the elements and we'll see where we are. So break, or debug. Break at 59. Run. Alright, so print heap.heap at 1 at price. Or print h dot heap at 1 dot price. Oh, god damn it. Print h dot heap at 1 dot price. Dereference a generic pointer. Oh my god. All right, I'm actually just gonna, instead of popping them, I'm just gonna go through the array. So mheap dot heap or h dot heap at I, and then we'll see what happens. So run. Didn't like something. All right. Should make this 1 and then less than or equal to 10. Break 59, run. Step into the print. Print gift val dot price 0.5. Right, step. Good. Alright, 12. 1. 13. 98. 15. 10. 102. 10. I may have messed up the arithmetic here. When we added the procedure, all right, we add the 234 and it has to swap with the 1129. All right, you know what, let me go into the print method, or into the compare method, and I'll print out what it's comparing. Or not compare, but the entry compare. So print f %d compare with %d, and I'll pass an I1 and I2. Zero, 12, 1, 13, 98, 15, 10, 102, 234. I could be wrong. No, wait, but it's still, it did, no, it still printed out in, okay, it printed those out properly. You know, let me just go back to adding 234. So 1129. So we add, after we add the 13, we then add, oh, I think I messed this up. We add a 234, and then we add a 98, which is then swapped. Okay, I think I messed this up. Yeah, okay, that is right. 234 1129. Alright, so that is right. But I think the popping is what is not going right. Okay. Yeah, because it only prints how many ever. Let me just clear this and run it to go. Oh, shit. Yeah, there's an infinite loop somewhere. Alright, so let me try breaking it inside this loop. So debug, break 61, run. Okay, so it's the one after 13. Alright, so step in. Alright, if return and heap.size is greater than 1, let me go to the pop method just to make sure this is all right. And then M heap down heap with the heap starting at index 1. Just stuff it in here. Print child 2, alright? Oh, you know why? Because this let me just make sure this is right. Yeah, okay. So in min heap dot down heap, I put the swapping only if it has a right sibling, so it doesn't work. So the conditioning in the while loop for down heap has to be if child is greater than or is less than heap.size, and then inside that if statement we have the call to entry compare with child plus 1 and child, and then outside of both of those loops we're then going to have the child swap if statements. So now if we run it, we should get all 12. So we get 0, 1, 10, 12, 13, 15, 98, 102, 234, 11, 29. And perfect. You'll love to see it. So yeah, that's a minimum heap, and you know, if you have this algorithm here is copyrighted by me, so you actually can't use this on Christmas morning, and if you do, I'm actually gonna, I will know, because I just know, and I'm gonna hunt you down, and I'm actually gonna take all your fucking gifts, just because, you know, just because it's my copyright. It's not copyrighted, don't worry. And I this isn't even my algorithm. I just learned it somewhere and thought it was cool. But yeah, you can use this on Christmas morning to assign values to your gifts. But you could also, instead of using price, you could use the love that it has. You could also use the size, double size. You could also have, let's say, you could have the amount of wrapping paper. You could assign values to certain givers. And you can all do that in the comparison function, which you can completely customize. So if we had, in the comparison function, we only compare the prices, but we could calculate separate values based on the givers, on who gave it, because, you know, certain people give worse gifts, and that's just like, that's okay. You can just straight up create bias against that person. So if the value is less, you want to get those presents out of the way first, and then you can open up the more valuable presents after. Or, you know, you could also, another good comparison would be, the amount of time it took to arrive, or the amount of demand for it, but you wouldn't know that. So this would have to be created by the parents. So the parents could just have this program running, and they could say add a new present from blank to blank with such and such value. You know, let's actually, this is not, this is no longer in the scope of the minimum heap, but it's a little experiment. So we will have a while loop. Or so actually just delete everything in the main loop, but the allocation and the freeing. So we'll have a while true. And we'll have, so we want to take input from the keyboard, and I might be forgetting how to do this, but I believe, so we'll just say printf giver colon, and then, you know, we'll just have the values, or let's actually create a gift first. So gift pointer new gift is equal to malloc size of gift, and then the printf giver. Oh, we actually need to include standard lib. Or while 1, because true is not a thing, or boolean is not a thing. It's not a type in C. So printf giver, and then we want to take it in, so scanf, and then we the format is just %s. Or let me actually see if we can do this in one line. So just scanf %giver, and then %s, no new line, and then we just pass in new gift dot giver, and then scanf receiver %s new gift dot receiver, and then scanf price %f new gift dot price, and then that actually has to be a reference to the price. And then we add the gift, so min heap _ add new gift, and the value will be, or sorry, add, and we pass in a reference to h, and the new gift will be new gift, which is already a pointer, and then we'll print out, we'll just print out the values, or we'll actually just call the print gift function and pass in the new gift. And then outside of the loop, we can just print a few equal signs just to divide it, and then we'll print out Christmas morning. And then we'll say we'll have a placeholder for the thing, so void pointer current, and then while current equals min heap _ pop, pass in reference to h. Now for this while loop, the condition, do not put an equals because we're setting the value of current, and then we want to use the value of current in the condition. So if this is not null, then we want to go into the loop. So we'll just go ahead and print gift and pass in min heap _ pop, or sorry, just current actually. Oh, we actually don't have a thing here to break. So I'll say I also have to include string here. So after we get the giver, we just want to test the length. So if there's no length, then we just break. So if strlen of new gift dot giver, or if not actually, because then it's going to be 0, then just break. Alright, so let's run. Okay. I don't think it's liking this, so maybe we do have to separate the printf statements from the scanf statements. That's fine. Alright, now that I separated that, let's try this now. From Michael. Oh, fuck, it broke it. I'm just going to see if it actually registered any input. No, it didn't. No. Maybe I have to pass this in as a reference. That could be it. Nope. Maybe I need to make the separate or surround the new gift dot whatever with parentheses and then get a reference. Let's try this. No. Let me just try printing out the string length here. Oh, it does. Oh, wait, that wasn't. Sorry. There we go. What the fuck? I think I need to debug this. Break 48. Run step over. Print new gift dot giver. Address out of bounds. Okay. Is it? It's not liking. Let me print new gift to see. All right. So new gift actually is something. But it's not liking that I'm reading to a string. All right. Maybe I need to just get values for the characters. So char pointer giver, and then this is not going to work because giver, it doesn't have any length. Oh, son of a bitch! All right, giver is equal to malloc 100 times the size of char. And then we have to copy it over. So str copy. Destination is new gift dot giver, and the source is just giver in the main file. And the same thing for the receiver. I wish I could. Can I drag this window over here? No, I can't. It's still not liking it, son of a bitch. Uh, 48. Alright, so giver's right. Okay, so it's segmentation. Son of a bitch. You know, I think we just have to make gift, the structure, have the character arrays just have to have a default length of 100. Or let's say 50. So they can actually have some a pointer value. So now that they actually have a value, well, you know, it kind of... yeah, it kind of did make sense, because when we just allocated it, these were just garbage values, so they didn't have any length or anything. But now we should be able to just go scanf straight to new gift.giver, and then scanf straight to new gift.receiver. All right. Oh, okay, so it's not. All right, so it doesn't like. All right, so it's not getting this float. So maybe this. Nope. Alright, maybe let me just create a temporary variable. Double price is equal to 0.0, and then I'll read into a reference to price, and then I'll just set new gift dot price is equal to price. And then that should be good. Nope. What's going on here with the... Let me try printing out the price that we enter here. Okay. It's not even reading it into the price. %F is the double value, no? Maybe I have to make this a float. That might work, I don't know. Okay, alright, so making it a float, I guess, worked. It didn't like the double for some reason. Don't know. Oh, you know, that might make some sense, because a double is 8 bytes, and we're reading in a float. And we pass in a reference, which is 4 bytes, so it might only be passing in 4 bytes to wherever the reference is. Alright, so Michael gives mom a gift worth $5. Then mom to Santa. Should be the other way around, but you know what? Maybe we're feeling generous. And you know what? The value here is actually $1 million because it's just cookies. And cookies are amazing. So mom gave Santa a gift worth $1 million. Then we'll say dad to the ghost gives it worth $12. And then maybe Saint Nick, not to be confused with Father Christmas, to we can't have two things in here. Okay, I'm not really gonna give a shit about the input. This is just a quick little exercise, but it should be get line actually. And I'll fix that in a second, but I just want to make sure this all works. And then from Nick to dad, and it's worth 123.05. And then break. Uh-oh. Ooh, there's a problem with the input here. It doesn't just... So I guess I do have to do get line. So... get line. Or is that a thing? Oh, this is... You see, I'm not the most well versed in C input output. So let me just try doing something here. Holy shit. That is not right. So let me say this. If I'll just say str compare new gift dot giver and q, and if that is equal to 0, so if not that, then break. Run q. Fuck me. Alright, maybe this while loop condition isn't working, so let me just... I'll just do it. I'll do the assignment outside of it. So the it should be void pointer current is equal to mheap.pop or mheap.pop, pass in a reference to h, and then while current, and then print gift current, and then current is equal to mheap underscore pop, reference to h. Nope. Am I returning something that's valid? Alright, in pop. Maybe I have to add an extra condition here. So else if heap.size is, or is else if not heap.size, then just return null. Because it's assigning it memory, and that memory is just garbage memory, so it's not going to be null explicitly. So it has to, we have to explicitly return null if there's no size. So now run. Q. Alright, good. So now let me try this here. Run. We'll do from the ghost to dad 12.5. Then Santa to dad. Dad's getting a lot of gifts today. 17.89. And then from dad to mom, let's say $1,000. And let's say dad to Santa. Then these are the cookies. So $1 million. And then quit. Okay, so 5, 12, 17, 1,000, $1 million. Fuck yeah. Alright, so that's a little something there. Got it. Got a little input system going. Let me just test this one more time. Five and 12. All right, perfect. All right, so that's a minimum heap and then a little play for an input system, but it works, which is all that matters. So that's all I have for you guys today. Enjoy your Christmases. Merry Christmas. Happy holidays. We got through the year somehow. And you know what? You're welcome to use this algorithm. I probably should post this on December 24th so you can give this to your parents and let them use it, or let them do it the day before. And then while you're at it, just teach them how to code in C. You know, because that's an infinite gift. Like there is no gift that's like that. Is infinity is that a thing here? So from child to parent is infinity, or INF? Oh, 0. Okay, no. So yeah, that's pretty much all I got for you guys today. Well, once again, enjoy your holidays. This is pretty cool stuff. And then I'll be back within a week with some newer OpenGL content, and then new math library content. I've been loving doing a lot of shit in C recently, just because of all this stuff, and you can like explicitly allocate and deallocate method or memory, which is really cool. So yeah, enjoy yourselves, stay safe. If you're going to families, just stay safe. But I think you should still see family. Just make sure you're safe. And then yeah, until next time, until the new year. Or I actually think I have another video coming out before the new year. But until then, enjoy yourselves and have a good one.